So now we will discuss how to penalize insertions and deletions in sequence alignment in a more sophisticated way. Previously, we used native scoring for indels, where we assigned fixed penalty sigma to each indel. However, this fixed penalty isn't good to represent series of hundreds of consecutive indels. And we will call this sequence of k consecutive indels as single evolutionary event gap, rather than many evolutionary events of small insertions and deletions. To model this situation in sequence alignment algorithms, we will use a fine gap penalty, where we use two constants. One is sigma, which is gap opening penalty, and the second one is epsilon, which is gap extension penalty. And usually sigma is more than epsilon, since starting a gap should be penalized more than extending it. And the formula to calculate penalty for a gap of length k will be sigma plus epsilon times k minus 1. So let's take a look now how we can use this in our Manhattan grid. Previously, we had a single edges with weight sigma to represent insertions and deletions, and these edges were horizontal and vertical edges in our Manhattan grid. Now we can add more edges. For example, we can add an edge of a weight sigma plus epsilon, which will represent a gap, a single gap of length 2. And for our Manhattan grid, we actually need to add a lot of these edges. So we need to add separate edge for all gaps of length 2, edges for all gaps of length 3, and more, and we will need to add it vertically and horizontally. How many edges have we added to our graph? Actually, we added edges proportionally to n cube, where n is the length of sequences which we are trying to compare. Since sequence alignment algorithms runtime is proportional to the number of edges, our algorithm will be quite slow. It will run proportionally to the n cube. How we can improve this running time of algorithm? We can split our Manhattan grid into 3 levels: bottom level, middle level, and upper level. Bottom level will represent insertions and will contain only edges which goes vertically from node to node. Middle level will represent matches and mismatches and will contain diagonal edges. Upper level will represent deletions and will contain only horizontal edges of our graph. And still, we need to find a path between top left corner to the bottom right corner. And we can move in our Manhattan grid, but we also can move between these layers of the grid. So, for example, we can take one edge diagonally. And now, if we want to make insertion, we need to move to the bottom level, take one edge there, and move back to the middle level. And these two edges will represent a single gap with sigma as a gap opening penalty and epsilon as a gap extension penalty. After that, we can continue moving on the middle level. For example, we found a match between our sequences. And then, if we want to represent deletion, we need to move to upper level, make some movements there, and go back to the middle level. And we can finish our path. To model this mathematically, we can have 3 different equations for dynamic programming for each level. And lower level will use information from lower level itself, and the middle level. Middle level will use information from all 3 levels, and upper level will use information from upper level itself and the middle level. How many edges does this 3-level Manhattan grid have? Hint is that degree of each node is quite small. So each node in this 3-layered Manhattan will have only 1, 2, or 3 neighbors. and number of edges is proportional to the n square, so the runtime of this algorithm will be the same as before. But currently we can use more sophisticated fine gap penalty than the native penalty which we used before.